Good morning, all. Okay. So today the fourth day is over. Today is the fifth day. Tomorrow is the last day. Okay. So with all your support and the support of the CUK, we have came to the fag end of this workshop training program, faculty development program. And today we have with us Professor Chandra Sekhar. He is a professor in Department of Electrical Engineering, NIT Delhi. He started his journey as a assistant professor from NIT Srinagar. Then he moved to NIT Delhi, and now he is a professor in NIT Delhi and dean planning. Okay, and he regularly visits our institute. This is second time he is visiting to our department, and all support in research, development, academics. We have got lot of support from Professor Chandrasekhar, very kind-hearted personality. As far as research is concerned, he already completed 2 SIR projects, and he has around 50 plus publications, patents, lot of contributions he has done in the field of electrical engineering, especially power electronics and electric drives control. So we thank sir for coming here, and I request Professor Amrendra sir to invite Professor Chandrasekhar with a bouquet. Thank you, Amrendra sir. So now I request Professor Chandrasekhar sir to start his session. Okay, sir, this is.
Yeah. Good morning to all of you. I thank you for inviting me for this AICT workshop, 6 days workshop, and especially A and ML electrical vehicles control. Uh, Although I came yesterday to deliver this lecture, I'm working, especially from last 4.5 years, I'm working on these hybrid electric vehicles. Now, once I shifted to Delhi, now I was more inclined to this climate related, how these electrical drives will affect the climate related things. Because every day you are seeing the climate issues of Delhi and air quality index of Delhi. So once I landed in Hyderabad and also landed in this place, I have taken a strong breath, and today morning also I had a walk around more than 4 kilometers. This was required for me also. That's why I came and visit, especially in the month of November ending and December and January. So these are the tough time for Delhi people. So, and it's my privilege to be part of this program. And without delay, I will start my presentation. Turn off the light. So my topic is hybrid electric vehicle evolution in the 21st century towards green and sustainable mobility. So this title itself indicating that it's a like a sustainable development and green technologies. Now most of the electrical engineering, because we are the faculty members of electrical engineering, and now it is a time to switch, or it's a time to change our curriculums and also educate our students on the advanced development areas. And most of the things, for example, I graduated in 2005 as electrical engineering student, BTech, and I studied like DC missions and all the conventional motors I had already, and my teachers also given the same topic to everyone. Like if you see the present technology with respect to this AI and ML and computer science, every 6 months or maybe every 15 days we are getting one software update. So then only our mobile is working properly. So why this electrical engineering? Most of the students, they are not choosing this particular program because we are not updating ourselves and we are also not updating our curriculums. The simple example is, I told you, I studied DC motors. Now I am teaching the DC motors. Maybe my son also will study the DC motors. So then where is the curriculum revision? And where is the new technologies they are studying? So if you take a special electrical missions as a course, or if you take a special electrical missions as a elective course, or if you keep electrical missions, special electrical missions as a last unit of electrical missions subject, so then most of the students and most of the faculty members, maybe because of the syllabus coverage, we rush to close the syllabus and we are not giving much emphasis on particular topic. So now it is the time to change our, and it's the time to upgrade our skills on the future technologies and what industry is exactly looking. After I started today morning, I had a discussion with Professor Amarendra also. After started working on these EV motors, the progress of my personal research is very good. This is what I am sharing. Whatever the work assigned to my BTech students and MTech students, so that simple work is going to the patent. So my students, he is working on one technology, or he is designing one particular motor, and the same motor now I am going for patent. And recently I started my startup, private limited, Advanced E-Mobility Technologies, with that patent only. I have granted one patent, and then immediately I started going with the same motor. So why I am sharing this is, there is a lot of forbidden in this particular area. The very few faculty members or very few researchers, they are involving in this particular area. So that's why it is now, it is the now the time to change our research topic, or it's now time to work on this particular topic. So everybody has to take an initiative, whatever the level. If you are a faculty coordinator, or you are a HOD, or you are a professor, or you are a student, you should put in your words towards to this particular topic. So that's why without delay, you see, whenever if you want to do the research, you first time identify the potential of that particular research, and what is the importance of the particular topic with respect to our Indian scenario. So you see, I have already considered the India climate-related commitments. This is already the government of India has given the commitments. So this is the climate-related commitments. Because I told you I am in Delhi, so definitely I have to take this climate-related commitments only. So how an electrical engineer will related to this climate-related commitments? You see, whatever the commitments given by Honorable Prime Minister, these are the 5 commitments they made in the conference, the central worldwide conference. So you see that the India will reach its non-fossil energy capacity to 500 gigawatts by 2030, and to meet 50% of its energy requirements, like I am talking about with the electricity point of view. So the renewables by 2030. Again, the 50% of energy requirements is reaching the target is by 2030. And to reduce the total projected carbon emission, this is important. So the climate related, mainly the carbon emission. So how to reduce this carbon emission by 1 billion tons through the period of 2022 to 2030. And another one is, the fourth one is, by 2030, the reduction of carbon intensity of its economy by less than 45% with respect to 205, with respect to the 2005, I think, basis. And already most of the countries in the world, they committed for target net zero. The India is also committed 2070, so that we call it as a India will achieve the target net zero. So by 2070, what is this target net zero, and what other countries they said? India is committed for 2070. So in the world, there are more than 260 countries. They already finalized their net target, and then we will see what is their milestone, what is their roadmap, and all these things we will see. So this is the climate related commitments already given by the Indian government. Now you take any, these are my objectives. I am considering my research. These are the objectives, and I have to take any one of these point through my research, how I will achieve. So definitely you see, the objective is not a 1 year objective. It's not a like 10 years objective. It is like 2070 or 2030, I think. So to achieve these targets, first I need to check what type of resources are available in India, why they made such type of strong statements. So that's why I have already taken in the India where in the actions. So if you see here, so I can say, so the fourth largest crude oil refineries are available. Of these two lights, and also the third largest consumer of energy. So in the world, thank you. In the world, third largest consumer of energy, and fourth largest crude oil refineries, and third largest crude oil consumer. So you see here, so most of the like energy related commitments, the India is a third option, or maybe okay, maybe it is like first or third option is only there. It means we are consuming energy in the third position, and we are also consuming the oil in the fourth position. So like this. So what is the importance of this particular slide is, so while seeing this slide in the entire world, so where is our India? So what are our energy requirements? And also you can see the India evolving primary energy matrix, energy maximum baseline. You can see the oil, nuclear and natural gases, and hydro and coal as well as renewable energy. So you can see the primary energy consumption to double by 2050 in all scenarios. So if it is like 20% or it is like 6% in 2018, now it will be approximately double by 2050. The share in the global energy consumption to rise from 6% in 2018 to 12% in 2050. So that's why we have to understand what is the present situation of India with respect to energy consumption and crude oil refineries and all these things which are available as with respect to energy related issues. And now you see the roadmap, the India energy emission as well as target. So this is the roadmap based on the climate related commitments. The Indian government already given climate related commitments, and there are certain milestones and certain targets. And you see by 2030, whatever the 5 objectives I proposed in my first slide, and this is the time like 2030, I want to achieve certain level of objectives, and 2047 certain objectives, and 2070 certain objectives. You see 2030 like 500 gigawatts of non-fossil capacity, and 50% of it installed capacity from non-fossil fuel cells, and reducing the emission of intensity like GDP to 45% on the basis of 2005. And like you see the energy independence. So this is also one of the important. So 1947 we got independence, but 2047 again now the energy independence. It means we don't want to depend upon whatever the things we are purchasing. We are purchasing the vegetables daily, and we are also purchasing the electricity daily. But now if you see most of the houses, they are only grooming the natural farming and getting the like that. The energy is also everybody will generate from their own, and then that is energy independence by natural resources only. And net zero target, the target, this is one of the major uh, point. Every climate related engineer or any all engineers, they are working how to achieve target net zero at 2070, like the carbon emission, how to neutralize this carbon emission. So thereby we will achieve the target net zero. So there are different sectors to achieve this, and electrical engineering sector is also one of the prime sector to achieve this net target. And you see, to what is the commitment of other countries in the world? What is their target? You can see the net zero targets. The India has committed like 2070, and USA is. These are the some of the major countries I enlisted in this particular slide. You can see the Germany. I think they are far ahead of all the countries in the world, like 2045, because they already started their the primary objective or their intention is by 2025 the four-wheeler propulsion, whatever the transportation is 100% electrical. Don't go for either IC engine based or petrol or diesel or gases. So they are just going with the 100% electrical. So that's why the first target is 2025 for electrical e-mobility application. Almost they achieved. Norway is almost 90% they are doing. So Germany is 2045, and rest of the countries like this. This is the target net zero. Net zero targets were achieved. But India has little bit late compared to other countries. But now again, it is our responsibility to come as early as possible to achieve this target. And then the pledges, the pledge for net emission, net zero emission. So what is this net zero target? Why people are working on this particular area? So I have considered there are so many sectors uh, in the net zero target, but I considered here the majorly 3 points. The first point is this, I can say 100% electrified sales that introduces battery, plug-in electric vehicle, plug-in hybrid electric vehicles, fuel cells, and this is the first area I am focusing. Another one is 100% zero emission vehicle sales. This is the second target. And the third one is, and all these two things, if I follow these two things, definitely I will get it net zero pledge, like carbon neutrality and no more greenhouse gases emissions. So this is the major point. So these are my 3 targets and 3 objectives again. And then to achieve these targets, again the world has already committed the roadmap for from 2025 to 2070 as per their targets. You can see there are different countries. If you take Norway, they already started on 100% zero emission electric vehicle sales by 2025. So Norway has banned all IC engine vehicles. So all vehicles are like they are saying now hybrid electric vehicles, plug-in hybrid electric vehicles they are using, like battery operated vehicles they are started already. So like this, the different countries they proposed about these 3 objectives, and these slides will shows that our India is also, see now 2070 we made the condition like they are saying that 100% electrified sales. See now everybody in the market, there are big players in the market like Tata Nexon or Tata Motors, MG Motors. So these are the company, they already invested a lot of amount on the research for getting like 100% electrified sales. Okay, so now you also see the major targets about these pledges, different countries and the roadmap. And now again, if you want to go in detail further, uh, the world is moving towards the net zero, with many countries are already setting their targets. Like over 67% of global GDP is now covered by the net zero targets. And more than 100 countries in the world, they committed for net zero carbon target by 2050. And it is expected further increasing by the conference, which will be held on next year, April. So now, as of now, 100 countries already they committed for this net zero target. And 56% of top world 250 companies acknowledge the risk of climate changes in the financial reporting. So this is also one of the major point we should also think about it. 56% of the top companies in the world, they already addressed these climate related commitments. They acknowledged these climate related issues, and now we are working. And then more than 100 USD were globally invested in decarbonization effect by 2020. It's already people are working on this. And limited global warming to 1.5 degrees centigrade requires the CO2 emission by fall of 45%. So this is the 2030 target. So where the world is moving towards with the percentage of targets, they are moving like this. And coming to our actual scenario, it is not a new topic. Electric vehicle is not a new topic. It is already started long back. So like you can see, 1837, this electric car has begun in the Scotland. So it is like later on again it is moving to 1884, like automobile cars, London, UK. And in USA, 1890, they already started like 6-seater with a speed of 14 miles per hour. So it is not a new it's not a new invention. It is already existing invention only. And the thing is how you are modifying the things, how based on the today's comforts, how we are doing the different comfort zones as per the customer. And these are the various types of motors, because now electrical vehicle, the heart of an electrical vehicle is also decided by the battery. As battery is the secondary, but the primary is the motor point of view. The DC motor, I can say there are different types of motors that are used for EV application, electric vehicle application, that is DC series motor, brushless DC motor, permanent magnetic synchronous motor, three-phase induction motor. These are the, I think, first one and the fourth one everybody will know about. We are already addressing. And switch reluctance motor, flux reversal machine, linear induction machine. So these are the different electrical propulsion motors which are used for to propel the electric vehicle in a on road. So now I don't want to insist much about the DC series motor and also three-phase induction motor. Now it is the time to study about these are the courses. You see, if you see the advanced or maybe special electrical missions, the content is brushless DC motor, permanent magnetic synchronous motor, switch reluctance motor, or maybe servo motor. These are the things are there. So now my point, you please encourage the students or you revise your curriculum by emphasizing more on these advanced electrical missions, I think. And now you see, I don't want to discuss about this DC motor, DC series motor. Now you can see this brushless DC motor. So it's like the brushless DC motor is majorly using for three-wheeler application as well as two-wheeler application point of view. In the EV sector, there are two-wheeler application, three-wheeler application, four-wheeler application, and heavy vehicle transportation of heavy goods also they are using. So here, this type of DC series DC BLDC motor are majorly used for two-wheeler as well as three-wheeler application, and it depends upon the two types of construction. It has a two types of construction. One is outrun type BLDC motor, another one is the in-run type BLDC motor. So what is this outrun type and in-run type BLDC motor? This BLDC motor is business is majorly on permanent magnetic materials. It's like permanent magnet. How best we are having a permanent magnetic materials in our country, so then we will use this one. So in-run, what is this the outrun type and in-run type where we are using exactly? Let's go in detail. So this is the outrun type BLDC motor. So this just like as it's a hub type of motors. It's a plug and play motors. So what I am saying in this motor is like it presents the motor is present outside the rotor of the motor is this is the rotor and the stator is inside it. So that's why we call it as a outrun type BLDC motor, and it is like it's the weight of this vehicle is very less. That's why we are using this as a e-bike application. You see in the e-bike application, like two-wheeler application, the hub, this is the hub, I think. There is no gear mechanism and all. So just this type of motor is available in the market with 1500 to 3000 rupees. It is easily available on the market. You can just use. And these type of motors are mainly used for the Hulika and these are the lightweight speed applications they are using, two-wheeler application. What I can say is that just as simple as possible and hub type motor. And then what about in-run type? The in-run type BLDC motor, so this type motor is just like as our like conventional, it's look like as a conventional motors, like gear mechanism, shaft. So then whenever this gear and shaft, these things are existing, it's like that definitely it is like a bulky type. I have considered this is already available in the market also, like 48 volts to 96 volts, the range of the voltage, DC voltage, and 10 kilowatt. The maximum power is, the peak power is 20 kilowatt and the speed is 3000 to 6000 RPM. And the diameter of this motor is like 260 mm. I will tell you what is the importance of this diameter and mean length. So those two factors will decide. So because if you see the vehicle, it's a space requirement. Again, we need to put it the vehicle. You see the vehicle is like the size of the vehicle is also small, and you should also think about the motor size also. You have to house in the motor in that vehicle only. So that's why the diameter and mean length of the this motor also is one of the major factor. So my point here is this three-wheeler application manufacturing, this in-run type BLDC motor we are using. And like you can see the Goenka electric motors, so these motors are already manufacturing in most of the metropolitan cities in Calcutta, Mumbai, Delhi. So if you go to any market, definitely you will see the manufacturing of these motors in that areas. And you see, this is the structure, I think. So motor is sitting here and then gear mechanism. Then after that, it is attached to the wheel. It's like as the main drawback is a high cost and also size requirements. So these motors are mainly useful for, these are the like e-rickshaws application, the three-wheeler application. If you see in metropolitan, even in, I don't know, in Hyderabad also, the cost of transportation up to 5 kilometers or 10 kilometers, now these electric vehicle e-rickshaws are going, because most of the people, they are getting electricity subsidized power bills up to 200 units, there is no power. So that's why the government is also encouraging to go for such type of e-rickshaws application. So it is the time to start a startup, maybe in the campus, or maybe some of the students, you start manufacturing of this type of motors. I have already collaborated with some Punjab, like speed way electric vehicles. So they are already manufacturing this type of vehicles. The cost of this type of vehicle is around 1 lakh, and it depends upon 1 lakh to 1.25 only. It's like more than 4 people can travel. And I have also mentioned the maximum speed is 25 kilometers, and motor power is 1 kilowatt. And the dimension, that is the dimension also important point. I will tell you where the dimension will place major role. And then the maximum motor voltage is 48 volts. I already enlisted here, and this is 48. This type of motor only, the Golden motors, they are manufacturing this. So 48 volts we are using. So this is one of the prominent research. It's not research, it's already there in the market. But only the thing is how best you will manufacture and how best you will put it in the market. So maybe if you start in the city also by introducing this type of vehicles, definitely the people will purchase. And then you need to avoid the diesel autos, diesel and in Delhi also now almost 100% ban of these diesel autos. And now that's why the pollution is in the limited, even though after banning all these things, the air quality index is going to 500. But prior to that, it is was 1000, because now most of the three-wheelers are with these e-rickshaws only, like public transportation. And now again, this is about whatever we discussed about BLDC motor. I am not going in details about the BLDC motor construction control. My target is how to design a best motor which is possible to related to the climate related commitments, and also 100% sales of electrical vehicles in the market. So, and also it will also leads for achieving the target net zero, that is a neutralization of no greenhouse gases and all. See here, the surface mounted permanent magnetics and also interior or buried permanent magnetics. So there are two types of permanent magnets motors are available in market. So what is the difference? You see the surface mounted permanent magnet. So this is the rotor. On the outer periphery of the rotor, the permanent magnets are placed by putting the epoxy glue and then attaching to the surface of the rotor. So the structure of this type of surface mounted permanent magnets are, it's not a rigid structure. Okay, and then if you see this interior or buried permanent magnetic synchronous motor, so this interior or permanent buried magnet motors, this type of motor now they are using for Tata Motors, they are using MG Motors, they are using most of the electric vehicle manufacturers, they are using this type of interior buried interior or permanent magnet buried. So why they are using is, so they are considering, this is the initial thought for the Tesla motor or whatever the things. For my research also, this is the initial thought. What they are doing is the rotor, inside the rotor there should be some slot, and there we are putting the permanent magnets. So that's why we are buried inside the rotor. So that is, we call it as a interior or buried type of permanent magnetic synchronous motor. And this type will gives as a rigid construction, and the rotor, most of the rotor is surrounded by permanent magnets. That is also increasing the cost of the motor also. And these are the different layers or different. This is the structure of a interior permanent magnetic synchronous motor with different bearings and different steel plates and all. So I don't want to emphasize more on this one. And now you see, I started working. The major problem with respect to this permanent magnetic synchronous motor, or maybe the BLDC motor, you know, from the fundamentals of the BLDC motor, the torque produced in the BLDC motor is like a trapezoidal in nature. So whenever it is a trapezoidal in nature, you cannot expect a smooth motion of a drive. So we need to put some controller, and maybe you can get as a smooth torque. And even in the permanent magnetic motor, it is a sinusoidal in nature. The torque produced in the sinusoidal in nature. So that's why the permanent magnetic synchronous motors are more useful in the EV propulsion because of its torque production, and torque is a smooth torque is producing compared to the BLDC motor. But the problem in the permanent magnetic synchronous motor is the rotor is made with the permanent magnets, and those permanent magnets also not available in our India. We are getting permanent magnets either from China or from Australia. So these are the permanent rare earth magnetic materials, like nudorium iron boron or also samarium cobalt. So these magnets are majorly rare earth magnetic materials. So those magnets are not available. So now the best alternative, these are the another type of motor we call it as a flux reversal mission. So what is this flux reversal? This is also not a new concept. It is already since long back, more than 3 decades back, the literature is available, this flux reversal motor. And I am also start working on this particular motor from last 3 years. I have already listed some of the advantages and what type of things. So the thing is, this reverse enables the bidirectional torque production. So the bidirectional one, whenever this bidirectional torque production is there, so it will useful for both motoring action as well as braking action. So that's why I have considered this. And also, you also see the comparison of 3 double silent missions. The double silent missions, I have considered one is the BLDC motor, another one is the SRM motor, another one is the FRM motor. Okay, you see this permanent magnetic motor, this double silent permanent magnetic motor. So either it is a BLDC or it is a permanent magnetic synchronous motor. You can see this one. Okay. And you see here, SRM is a unipolar magnetomotive force, and the phase flux limited to one torque only. It's a one direction is possible. And that doubly silent permanent magnet is the bipolar. But whereas in the FRM motor, it is possible in 4 quadrants. We are getting 4 quadrants of energy possible. It's offering of the control of is also possible in 4 quadrants. But only one thing, whenever you are targeting some special electrical motors, some special related motor, the major issue with the special electric motors is how to minimize the cogging torque, how to minimize this pulsating torque. So there are different types of techniques that we will also discuss. And now see the principle of operation of this FRM motor. It is a very simple, like it's not a complicated to learn also, like a DC motor or induction motor. This is simple. So this permanent magnetic flux reversal motor, how the flux reversal is take place is, you take a DC motor, a shunt motor or series motor, whatever it may be, the pole shoe is there. So on the pole shoe, we are putting as some slots. And inside that one slot, there are only 2 slots in every pole shoe, not a pole shoe. So this is the pole shoe. Here I am putting some slot area, like a dusk type slot I am putting. And in that, permanent magnets are keeping. Instead of keeping the rotor, what I am doing is I am keeping the permanent magnets on the stator, but not completely permanent magnets. So this rotor is like a teeth. It's like a steel material. There is no winding on the rotor. Only structure, it is a teeth will be there. It's a lightweight rotor, but stator is a heavy. Heavy means winding and all are there. But in the pole shoe, what I did is some shell type it is there, slot is there. There we are keeping, in every pole shoe, 2 slots are there. In that one slot, I am keeping north pole, another slot is south pole. This is like a 2x3 FRM motor, 2x3 pole. It means 2 stator pole and 3 rotor teeth. There is no winding on the rotor. It's only just like as a teeth, as a blade, I think. I can say it is a steel blade with the teeth, I think. So then, whenever the torque flux is produced, then this motor rotor will rotate smooth, I think. So coming to the operation, how it will works, how the torque is producing. And it's also not a sinusoidal, it's a triangular shape torque is producing. But now, by controlling some power electronic device, you need to put it as a sinusoidal. It is a very simple compared to the trapezoidal or a square wave. When it is a triangular, then you should make some converter design, then it will be coming as a sinusoidal. But my target is, my objective, or I am working towards how to minimize the permanent magnets. How best you will minimize the permanent magnets, because the permanent magnets are not available in our country. So the heart of the motor design, especially the permanent magnetic synchronous motor or BLDC motor, more than 50% is housed with the permanent magnets only. So that's why here you see I am not keeping the permanent magnets entire rotor. My rotor there is no winding, only stator I am keeping two like a blades of the permanent magnet. So almost I am reducing more than 80% of the permanent magnets consumption with respect to permanent magnetic synchronous motor or BLDC motor. So coming to this here, what I am doing here, let us assume this is the initial position of the rotor. Okay, rotor initially, if you take one teeth one here, this particular teeth is 50% is aligned to the north pole and 50% aligned to the south pole. 50% is aligned to the south. This is the middle. So 50% is aligned to the stator, north pole, and 50%. So then the net torque, the flux linkages will be 0. So then what I mean say, it is 0 here. So the flux linkages will be 0. So now what I am doing is from that position A to 60 degrees I am rotating in anti-clockwise direction. So when I am rotating in anti-clockwise direction, 60 degrees, so my rotor teeth is aligned to one of the pole completely. You see here, this north pole is completely aligned to here, and also maybe again south pole or north pole is also aligned to here. It's like only 2x3 pole FRM motor. Maybe there are different types of structures. I will also explain in detail. So what I am doing here is, so one of the pole, it is completely aligned to the permanent magnets, north pole. So then the flux linkages will be maximum. It's going to maximum. And now from this initial position to 60 degrees, from here to again 60 degrees I am rotating. So from this point it is 120 degrees. So now what I am getting here is again 50% is again to north pole and 50% is south pole. So then what I am getting here is the torque production will also, the flux linkages will be 0. So then the torque production will be 0. Magnetomotive force and flux will be 0 at this C point, the flux linkages and position. And from this position to again 60 degrees in anti-clockwise direction, again my south pole is coincidence with the stator. So then what happened is, so it is like also ascending manner and descending manner. If I am rotating 60 degrees in anti-clockwise direction, maybe what I do, maybe you will have another doubt, sir, you are only targeting by 2x3. Maybe if it is a 6x8, or maybe there are different type of structures. I already enlisted here. You see this is 6x8, 6x14, 12x16, 12x10, 12x28, 12x40, 48x46. There are the different structures which are available. Either you can use these type of structures for electric vehicle propulsion, or maybe the wind energy conversion system. You can mostly this is also alternative. Usually people are working nowadays, up to now, this type of motors they are using for wind energy conversion system applications we are using. But now if you go with this 6x8 FRM motor, so that will also be useful for electric vehicle propulsion. So what they are doing is, if you see the construction of Tesla, that is interior permanent magnetic synchronous reluctance motor. So the Tesla motor, like Tesla Model 3S, so there what they are using is this interior permanent magnetic synchronous motor. They are also keeping that inside the stator pole shoe, they are also keeping the permanent magnets. The same structure they changed, but they name it as a interior permanent magnetic synchronous reluctance motor. But earlier it is already literature is saying that axial flux emissions. So axial flux emissions nowadays people are working, and you can see number of magnets requirement. The size of the magnet is also not big as compared to the PMSM motor. The magnets is increasing, but the size of the magnets also decreases, as well as you can see the speed with respect to 50 Hz, and gear ratio and torque decrease in cycle like this. So I have developed through the ANSYS software, like two models I have developed with my students, like 6x8 pole FRM motor, and also 12x16 model I have done. So 12x16, these two models I have developed, and one more model is 8x12. I am now started working on 12x. You can see here. So from this, you see this is my pole, and this is the winding on the pole, and pole shoe. This is my pole shoe here. So this pole shoe has magnets, I think. Here I am keeping the magnet, and this is the rotor. This rotor is like a teeth, rotor having teeth here. So 6x8 pole FRM motor. And then again, see, there are, I told you beginning of this FRM motor, what I discussed is, so how to minimize, the challenging task for this special motor is how to minimize the torque ripple reduction. So cogging torque, how to minimize this cogging torque. So there are certain techniques which are there in stator side as well as rotor side. Anyway, I have written one recent paper. I will explain after my lecture also. But I am targeting about rotor side techniques only. Stator techniques also I will explain. But in the rotor type techniques, rotor structures to reduce the cogging torque, there are three techniques I majorly literature is saying, and I have also used those three techniques for things. One is rotor pole pairing and rotor pole champering and rotor pole skewing technique. We know skewing technique because we are skewing the angle of 20 degrees or 15 degrees or 45 degrees with respect to shaft position. Anyway, but this, what is rotor pole champering and what are rotor pole pairing technique? You see, clearly observe the diagram. So this rotor pole pair, the structure of this is, I told you, a rotor is a teeth type. But see, every teeth is not a uniform dimension. It is a different teeth, I think. You can see this pole has a one width and this pole has another width. So this will also reduces the cogging torque production. The uniform air gap is there, but maybe sometimes you will also get non-uniform air gap in the rotor teeth places because of irregular rotor teeth. So that may also decreasing the cogging torque. It will also give one effect: the net torque will be coming down, and induced EMF is also maybe coming down. But my target is how to minimize the cogging torque. And another technique is rotor pole champering technique. So you see the bottom of each rotor pole, it is like a curvature in nature. It's not a straight. You see here, it is a straight line, a sharp edge here. Here I am getting sharp, but here you see it is a curvature in nature. It is coming. So that is also one of the factor to reduce the cogging torque reduction technique. So what I did in my ANSYS model, I have considered a normal rotor structure, conventional rotor structure, and I have performed the analysis and I have run the simulation after designing the ANSYS model, finite element analysis, Maxwell's equation. I done the simulation. This is the conventional, but this is the combined technique. So combined technique means here I consider rotor pole pairing as well as rotor pole skewing technique. So two techniques I compare. One is rotor pole champering, rotor pole pairing, one combined technique. Another technique is rotor pole champering and rotor pole skewing technique. Another technique what I did is pole pairing and rotor skewing technique. And the last final one, by combining all these techniques, again I have modified. So why I am doing all these different combinations is how to how best you are minimizing the cogging torque, how best you are producing the average torque. So, and without affecting the average torque, how to minimize this cogging. So that's the reason why I have done these techniques. You see, this is the 2D model, modified 6x8 FRM motor. So the flux density, magnitude, and also you also see this is rotor pole skewing technique, and two-dimensional magnetic flux, magnetic current density waveform, vectors. I think how it is producing. What is the field intensity of each motor and where the maximum field intensity existing, how the flux reversal is take place, all these things I have mentioned through the ANSYS only. And you come to this particular slide. What I have mentioned here, you see my table, I considered only rotor pole pairing method and only rotor pole skew technique and conventional model, because the conventional structure is not having any cogging techniques, rotor reduction cogging techniques, and this is modified model. Modified model is all these rotor pole pairing, rotor pole skewing, all the three techniques I combined and then modified technique. Now I have considered four parameters. One is flux linkages, induced voltage, torque, average torque, and cogging torque, peak to peak cogging torque. The skewing angle is I considered for 20 degrees. 20 degrees is my skewing angle. So in that case, you see, 20 degrees is my skewing angle. So the causing torque with the rotor pole pairing is getting very modified structure. See, here I am getting 0.72 Newton meters, and which is the best. And also another constraint I have, how best I am managing the torque, average torque. So my rotor pole pairing technique is giving the torque, but cogging torque is more. But here the cogging torque is getting low, and then minimum maybe the torque value is also coming less here. But induced voltage, you can also see how you are developing the induced voltages. The induced voltage in the rotor pole pairing is highest, I think, for the same type of structure, because it is giving the maximum flux linkages in that. So this type of analysis I did, and then after that I am going for the development of exact model through the hardware I think. So these are the different induced voltage of modified FRM motor, torque of a rotor pole skewing technique, and also cogging torque of modified 6x8 FRM motor, and the cogging torque for rotor pole skewing techniques. These are the 4 methods I considered, and 4 methods I did with the 4 parameters: flux linkages, induced EMF, torque, as well as cogging torque reduction. You can see the numbers with the visualizing the numbers also. So this is already I have made one patent, and now I started with the same technology, how to manufacture of these motors. I started one startup company through my student, and he is also one of the partners in the startup company. We are in the process of developing in the hardware, and once we will develop this and we will customize. Not only this 8 by 6, 6 by 8 FRM motor, another structure that is 12 by 16. So while again it is a complication, once we are increasing the rotor teeth and stator pole and number of magnets. So the thing is, this type of structure is majorly suitable for wind energy conversion system, and earlier structure is suitable for like electric vehicle propulsion. For EV application type we will use, and this is for EV, this is for wind energy conversion. So there also I have done the same input current waveform with respect to time, flux linkages, distorted induced voltage. These are the different things I given. But here what I did is, for 12 by 16 model, the permanent magnets I changed, I think. So what permanent magnets I changed is, because rare earth magnetic material and non-rare earth magnetic material. So when you talk about the materials, the property of the materials, rare, why it called as a rare earth magnetic material? Because of the Curie point temperature. So what is this Curie point temperature? If a magnet is kept under high degrees of temperature, it will automatically loses its permanent magnetic capabilities. So the temperature withstanding capacity for the niobium iron boron is 430 degrees centigrade. For samarium cobalt, it is around 330 degrees. So that's why these two magnets are rare earth magnetic materials. So they have highest Curie point temperature. So when the vehicle is moving, automatically the heat is generated inside the vehicle. It's a closed chamber. So once the heat is beyond the 400 degrees centigrade, then definitely it will loses its permanent magnet capability. Whenever it is losing its property, permanent magnetic property, there is no use of that particular model. So that's why the rare earth magnetic materials I considered, I considered for my research, niobium iron boron as well as samarium cobalt. I have also done like to compare the performance of different cogging torque minimization techniques for flux reversal applied to the medium speed unit generator. So I told you, wind energy conversion is also one of the application. Wind generators also one of the application for this axial flux emissions. So this is niobium iron boron, NdFeB, and this is the BH curve for this. And this is the ferrite, I think. This is the ferrite. The ferrite is a non-rare earth magnetic material. Ferrites are available in India also, but it is a non-rare earth magnetic material. But you see the BH structure with respect to field strength as well as with respect to flux density. So this will gives as the highest flux density compared to this ferrite materials. So what I did is I considered two types of motors. One is rare earth magnetic material, another one is the non-rare earth magnetic material. Then after that, I have introduced the techniques, rotor reduction, cogging torque reduction technique, like what I called as a pole pairing technique, as well as rotor skewing technique. Skewing technique also I introduced. So then I have designed two methods, and then I have done the analysis. So with respect to voltage regulation, power limitation, torque ripple, cogging torque reduction and efficiency. So this method I have done. So one of my PhD scholar has published this. I will also explain in the paper also how we do it, I think. So this is one type of work. This is one case we considered for our PhD. And this is another case, the cost effective also one of the point to compare the electromagnetic performance and cost analysis of rare earth magnetic and non-rare earth magnetic for flux reversal machine at 10 kilowatt power scale. So again, cost analysis. The rare earth magnetic material has the highest costly. This cost is another factor, I think. Cost analysis also we did, and then we given some of the conclusions considering the similar performance required, the torque density of non-rare earth magnetic material, like 51% maybe the cost factor is coming here. So we made some comparisons also, and then you can see here, this is my motor specifications. For any motor, the specifications is important. So the specifications what I considered here is for FRM motor characteristics. I told you samarium cobalt 24 magnets. This is the magnet number, and samarium cobalt 28 pm, nidorium iron 30 and nidorium iron 35. So these are the 4 magnets I considered for my simulation ANSYS model. And then again 4 parameters: input current, induced voltage, flux reversal, flux linkages, and torque also I have considered here. So these are the, you can see the torque, for per phase torque I have considered here. The per phase torque, it's not for one turn I think I have calculated. It's not per phase, one turn I have calculated. It is 1.4669. This is highest. These are the 4 permanent magnets are rare earth magnetic materials, and these rare earth magnetic materials are only suitable for now. Tata Motors is also using for the Nexon. If you see the EV vehicle, so there also they are using samarium cobalt. Even they are not going with the nidorium iron boron. So nidorium iron boron is the highest costly material. If you go with the nidorium iron boron, so then the vehicle cost will also increasing, because it has a highest torque, and maybe not only the torque point of view, the Curie point temperature is also one of the deciding factor for that. And these are the dimensions: rotor diameter, gap, all these stator side, shaft side, permanent magnets, how many we required. 12 permanent magnets on north pole and 12 permanent magnets on the south pole, like this. And this is the comparison. Now another type of research is going on in the research, especially this EV motor. So as I already told, BLDC motor and permanent magnetic synchronous motors existing in the market. The synchronous reluctance motor. What is this synchronous reluctance motor? So in the synchronous reluctance motor, for any electric vehicle, for smooth running, the noise is one of the factor. So noise reduction. So how this noise reduction is also depends upon the cogging torque only. So you see here, the noise level of BLDC motor is moderate and permanent magnetic synchronous motor is low, and for synchronous reluctance motor. So now what India is trying, our country, what we are trying is, so we don't have this permanent magnetic mines in our country. So now we only go with the synchronous reluctance motor, but the drawback of that particular is noise level is higher. So how to minimize that noise level? How to minimize that cogging torque? Once you reduce the cogging torque, so definitely the noise levels will be coming down. But here there is no requirement of permanent magnets. The synchronous reluctance motor has not required of any permanent magnets. It's just like as a conventional. That's why the currently developing technology as an alternative to the PMSM motor to counter the increased use of the magnets. And also the efficiency is also low, but now if you design a suitable power converter to improve the efficiency, then it's not a big issue. So then the major issues is, one is the application, another one is the noise level. Noise level is one. And the manufacturing cost, the main advantage of this reluctance motor, switch reluctance motor, is the manufacturing cost is less, because we are not using any permanent magnets about it. So the alternative of this PMSM motor and brushless DC motor, another one is synchronous reluctance motor. And another technology, it is already I have started and I have done some experimentation also. It is a linear induction motor. It is not already, it is existing. Most of the electrical missions lab also you will get this linear induction motor. It's not a new technique. It is already existing. But why I have introduced this one is, Again, for magnetic levitation application, we are using this linear induction motor. I designed a two-pole linear induction motor. I will show you how I have done. I have done in the hardware as well as simulation, both I did. So this is the rotor of the conventional three-phase induction motor. And now if you take A and A dash, these are the vertices, and then you can put it in a horizontal. So then phase A, phase B, phase C are there. So then this is the linear motor. The rotation of the motor, the conventional motors, it is a translational. But now if you talk about the linear induction motor, it's a linear. It's not a rotational. But whenever the challenging task in this particular motor is, and the controlling thing is, when the motor is in a circular, also it is a closed manner, the air gap flux and leakage flux, that doesn't matter. So that is not a problem for. But when you put it in the motor in a flat thing, the flux leakage flux will be more. And also end effect and edge effects are also there. So the end effect here, ends of the motor, how the torque will be producing, and edges also, what is the flux linkages, how it will behaving. So these things are also one of the research thing, how to minimize the end effect and edge effect torques, I think. So what I have considered, this is the principle of induction motor. I don't want to emphasize much, but here is, in this linear induction motor, the thrust force is the factor, I think. How much thrust you are producing. So based on the thrust, it will moving, velocity, how it will move, I think. So this is the design of linear induction motor. I have considered single-sided linear induction motor. There are two types of structures. One is double-sided linear induction motor, and another is single-sided linear induction motor. So this is the single double-sided. It means it is covered with the two stators, and the in between the slot is there. There the moving object is presented. So then that is a double-sided linear induction motor. Whereas in the single-sided, this is the primary and secondary. So then the electric movement of this body, the rotor, secondary is like as a rail, I think. You can consider as a rail, and it will move. So I consider the dimension size. Another thing is, whenever you are going with the hardware implementation, first you need to find out your stamping, lamination stampings. What is the dimensions? All the dimensions should be in the same manner. And then after that, so this is my dimension of the E type of laminations, and how much I have considered for single-sided linear induction motor, stator side, and what is the width of the gap, slot gap and all. So these things I have considered, and this is my rotor, aluminum wall, I think. I can say this is the stator and this is the rotor, and in between the air gap is existing. So for this also I have aluminum rotor, outer rotor. You can see here. So these are my stampings, CR and GO laminations, and all these laminations are made with the stamping. And you also see the winding arrangement. This is important. When you are doing the stampings and laminations and all, after that again, you need to put the winding details. So I have considered only two poles. One is north pole and the one is south pole, like that. Two poles I considered, and 12 slots, I think. 12 slots, and number of phases is 3. I calculated pole pitch, slot angle, full pitched angle, coil span and everything. The coil span is like 6 slots per coil. So and then after calculating this, now I have to go for the winding arrangement. So this is the primary setup what I proposed. So two coils. So this is coil A and coil B, and two poles. This is pole A and pole B. And you can also see 1, 2, 3, 4, 5, 6 coils, 6 slots in one coil, and another 6 slots in another coil. Total 12 slots are existing. You see this is my single layer winding configuration for a 2-pole 3-phase induction motor. So again, so whatever the winding diagram you are doing, the same winding diagram you have to here. You see here. So this is my winding, R phase, Y phase and B phase. Again R phase, Y phase, B phase. But this, and then again I am combining these two things to the motor, I think. Okay. And this is by winding arrangement. Then after that, this is the primary winding setup. Again, the designing of secondary rail. So how to, anyway, you are getting some force, you are getting some linear thrust. Then how to witness the force, how to witness the thrust. So definitely there should be some physical movement. So after giving some excitation and producing some flux, then some thrust has to create. So how to witness the thrust? So for that case, what I have considered is, so the secondary rail, so this is aluminum bar, and then I have created some wheels on this, and then this aluminum bar. So this is like I am considering as a locomotive, a trolley or vehicle. So then this vehicle will moving, I think. So again, what I did is, again I have given some static magnetic field excitation. So earlier you can see in the induction motor we are getting as a rotating magnetic field, but whereas in this linear induction motor, traveling magnetic field. So the traveling magnetic field is there. So that traveling magnetic we have to work out, and I have done some excitation currents also. The excitation voltage is 5 volts, DC excitation voltage, and the current for each phase is 2.5 amperes I have given. So these are the various currents. I think I have considered 3 currents. One is 2.5 amperes, 3.5 amperes, and 3 amperes. 3 currents I have considered. And how the flux density is producing by using some Gauss meter I have measured also. And this is my variation of the air gap flux density versus mean length of input current 2.5 amperes. So for 2.5 amperes I have considered for this. I am getting a sinusoidal current in the stator. So then after that, again what I did is I used the Gauss meter to measure the magnetic flux. So we have considered the we also find out how much flux is getting. So that's why we measured this magnetic flux for each pole. I think for each phase I think we have considered this. And then for different DC excitations, uh, what is the R phase maximum voltage, Y phase maximum voltage, and B phase maximum voltage? As I told you, I have considered 3 type of excitation. Although the current is 2.5, 3.3 and 3.5 amperes I considered, but the voltage is 208 volts, and almost it is 208 is the maximum, but 205 to 208 I considered. For this is my DC voltage I have given, and then after that these are the excitation voltages I am getting in each phase. Then after that, to measure the linear thrust or linear force, so again I have put some spring here, how much speed it is moving, how much force it is moving, sorry, how much force it is moving. So that's why what I did is, initially when I have manufactured this thing, so without putting this insulating material, wood type material, what happened is some magnetic locking is happening. So that's why whatever the excitation I am giving, so my vehicle, that secondary rail has not started moving. It is just stuck because of the magnetic locking phenomena. So to eliminate that magnetic locking phenomena, what I did is I considered so stator, and after that some wood insulating material. Then after that I am putting the electric this secondary rail. So then this is moving, I think. So this is the same experimentation we did, and then we found the different excitations, the speed, how it is varying. So that is also I have considered variation of the secondary velocity for various currents. Different currents I have considered. The input current is 5 amperes, 10 amperes, and 15 amperes I given, and then the speed of in terms of velocity we have plotted. These are the thrust and also speed characteristics we considered. And this is the final setup of this linear induction motor prototype what we did in our lab. So I have considered for the demonstration purpose in my lab, so like I have some mild steel material I used, and for there I am keeping all the stampings, laminations, and then this is my insulating material to separate this primary as well as secondary, and this is my secondary which is moving, I think. And these are my parameters and design specifications. So this paper is already we communicated to IEEE, and maybe it is a second revision is going on. What we did is, after implementing this, now we have done in the ANSYS model also, the same ANSYS model, the same structure we designed for ANSYS model, and we produced this same thing to patent also, the linear induction motor. We filed some patent also on it. Yes, I coming to this particular thing, the types of permanent magnets. So I told you the materials is the one of the important for every any understanding purpose. The material is also, you need to, properties of material is one of the important tasks. So what type of materials are there? Like ceramic material, alnico, samarium cobalt, niobium iron boron, injected mounted. So these are the 5 materials. So see, samarium cobalt and niobium iron boron, these two are the rare earth magnetic materials. So what is the, how you will decide it's the rare earth magnetic material? So the energy density, I can call it as a energy density, highest energy density. How you will witness the energy density? By seeing the BH loop, BH curve loop. The loop of a BH curve, it will shows that highest. For rare earth magnetic material, highest energy density is possible. And you can see this ceramic material is the non-rare earth magnetic material, and it have like low energy density and low mechanical strength. It's like brittle. The cost is low. The simple thing is low cost. This type of mines, this material is available in our India. We are already using this type of materials. Another one is Alnico. Alnico is also high cost, and like we can also say that low energy density. Low energy density means like pH curve, the product of BH curve we call it as energy density. So that's why we are getting low here. And you see the highest temperature stability is possible for Alnico material. And you can see the samarium cobalt. Samarium cobalt is highest energy product, higher energy density and high corrosive resistance, high temperature stability. So all these, but only the thing is low mechanical strength and highest cost. The cost is a factor. And same thing with the nidarium iron boron. It's a very high power density compared to the samarium cobalt, but high costly here. The costly point is there, and also the temperature, moderate temperature stability is there. So, and then this is also injected molded is also like a uh, non-rare earth magnetic material. So these are the 5 materials I consider. And again, I told you in the beginning of my presentation, the mines where these non-rare earth magnetic materials are available in the world. You see here that China is having highest, I mentioned the global production of the share. The China is getting highest, and then rest of the countries, Australia is also have, and South Korea, and maybe this is the structure where the global magnetic production locations in the world map. And you also see this side, if you take a electrical vehicle or electrical motor, in that electrical motor, what is the share of these permanent magnets? The share of the permanent magnets is approximately 53%. The magnetic share is 53%. And rest of the things are like 47%. So what are the rest of the things like stator iron, stator copper, housing, rotor iron, shaft and bearings. So this is the structure of percentages. But you see more than 50% the magnets are only presented. So that's why the rare earth magnetic materials, we are depending upon the production of other countries. So that is also one of the key factor. I told you, however, both these technologies comprises the magnet is the key subcomponent, which is the use the rare materials considered the China only. And then this is the development of the magnet-less motor. So this is also one of the research topic. Also, I'm floating to all the faculty members. If you want to develop the magnet-less motor, so the depending upon the rare earth magnetic materials. So what we call it as a synchronous reluctance motor. I already mentioned the synchronous reluctance motor is not using the permanent magnet. So it is called as a magnet-less motor, and reducing the dependency on the rare earth magnetic materials. Currently, the BLDC motor and permanent magnetic motor, we are using the rare earth. So this is also one more thing I have mentioned. And also the thing is motor control is braking mechanism and regenerative braking. Anyway, regenerative braking mechanism also we require. And see again the types of EVs are available in the market. So you know there are 4 types of EVs are available. One is like battery operated EV, hybrid electric vehicles. The hybrid electric vehicle, 2 structures. One is hybrid electric vehicle, another one is a plug-in hybrid electric vehicle. Another one is fuel cell electric vehicles. So you see here, so the battery electric vehicle, what is the back? Just you can see the Tata Nexon and MG motor is the plug and play. When you put the vehicle and its battery will be charging, and then after that your vehicle is moving. So that we call it as a battery operated electric vehicle. And then plug-in hybrid electric vehicle, both electric motor it will run as well as IC engine also it will run. And then hybrid electric vehicle also same structure. The fuel tank is there as well as electric motor and batteries are also there. And fuel cell, it is like as a hydrogen tank. So in future, people are also witnessed the problems of energy consumption. Now the technology is going with respect to fuel electric. This is like fuel cell electric vehicles. Instead of going to this battery, so now the battery is also another thing. So like if you see in our household purpose, what we are using some gas cylinder. So the same type of structures we are preparing to store this hydrogen gas, and then you can keep in our dicky and then you can start running. So this is another alternative, and people are also using this type of fuel cell based electric vehicles. So you can also see what is the structure, what is the difference of this battery electric vehicles, plug-in hybrid electric vehicles, EV electric vehicles, and fuel cell based. So I told you it is like both oil as well as electric connection. So here it is only with this hybrid electric vehicle. So plug-in electric vehicles means you need to go like what we are having like CNG based now. The CNG you can sometimes you may go with the CNG and sometimes you may go with the petrol. The same structure here also. Sometimes you will travel with oil and sometimes you may go with both the options we are getting. So nowadays these are the popular now. So after this CNG, the market is also going with this type of MG motors. If you go, they are manufactured like this. And also like this is only hybrid oil like petrol you are injecting. So then after that the battery, when the wheels are moving, the battery get charged. Then after that you may go with the electric motor also. Then this is the hydrogen tank like fuel cell based. So these are the different structures what we are using. So this is battery operated electric vehicles are 100% electric motors and it's rechargeable batteries. And like 100% electric motor with a fuel cell conversion. So I have mentioned with the different structures what we have: fuel cell conversion, hybrid electric vehicles, and plug-in hybrid electric vehicles. And then these are the cases, I think. And then again, if you see electric vehicles, which company they are manufacturing, the main components and working principle and the examples. Toyota Prius hybrid, they are using like hybrid electric vehicles, and Toyota and Honda, they are working on hybrid electric vehicles. And this is the plug-in hybrid electric vehicles. So like almost the BMW, Tata Nexa, all these companies, they are also using this one. And fuel cells, I think now the Toyota as well as Hyundai, these people are now working for this fuel cell. Now the technology is, we are talking about renewable energies. Now renewable energy is there, but now when we are coming with the actual renewable energy, now we are talking about the green hydrogen technologies. The green hydrogen technology is also an example of this fuel cell, this hydrogen tank. So once you take as a hydrogen tank, then you will get your vehicle will moving. So this is also another case. And again, before going to this FRM motor, flux reversal motor, I started initially working on switch reluctance motor, and I got funding for this switch reluctance motor, plug-in hybrid electric onboard charging facility through the advanced research grant, like we called it earlier, it is a core research grant. So I have developed this same structure in my lab, and my scholars are also working. So I have considered like the structures, different structures, like two-phase.
Take a short break for tea.
Acha, 5 minutes, huh? Okay, okay.
1 hour.
Okay, okay, no problem. Okay, okay, okay.